Hi, Caroline. Can you
Hi.
hear me well and see the
Very,
screen?
very well. Yeah.
Thank you very much. Uh, I'm very glad to be with all of you. I was very impressed by the previous presentation by Professor Bazan, and I'd like to add in the beginning my gratitude to NUS. I think this is really a great university, and the way it is handled is really spectacular. So I'm talking to you about quantum mechanics, and this is a little bit a far-fetched topic for many people. Uh, there is an area of mystery around the word quantum, although many of the things we have been hearing are related to quantum physics at the most fundamental level. So I'm speaking today on behalf of the Center for Quantum Technologies. So this is a place where we are trying to understand in depth what is quantum mechanics and what are the ways we can use them um, in our um, for improving our lives. So we are a center that does basic curiosity-driven research and also applied research, or let me say the first steps to apply quantum mechanics um, to our society. So my presentation is a little bit different because I, rather than telling you how useful things are, I want to give you a perspective of what what is quantum mechanics research nowadays. And for that, I prepare something divided in 3 steps. The first is to tell you a little bit about the edge of knowledge in this microscopic world. Second, I'd like to tell you a little bit within this context of the edge of knowledge where CQT stands. And in particular, I want to bring to you the idea that CQT is a place where we generate this kind of knowledge, this knowledge at the edge. And finally, I will try to produce an invitation for research for the students. Okay, so this is my little plan for these few minutes that we are talking. So let me go to the edge of knowledge. Let me put a little bit of context. So I will go very back. Okay, I will go very back. Uh, I could go, to the pre-Socratic schools in Greece, to the Persian world, but let me make it a little bit more concise, only 4 centuries, 3 centuries and a half. Let me start with Descartes, okay, the French philosopher René Descartes. This is early 17th century. Why I bring this little line of progress to Descartes? Because Descartes is the person who proposed the separation of studying the physical world from the human mind, from God. And this is really a fundamental step because it allows the study of the physical world without the need of understanding the other things, neither God or the human mind. And not only that, but Descartes also proposed the reductionist method. So he was a rationalist. No? So he said, if you don't understand the problem, reduce it to the elementary parts of it. Try to make progress, and only later you will put them together. So these ideas were so successful that in the very same century, later in the second half of the 17th century, in 1686, you have Isaac Newton producing the first postulates for the mechanical world. You see, you've reduced every knowledge to the basics. And that was such a successful idea that you can even trace science in the 18th century to trying to apply this kind of reduction and to everything was possible, okay, including as Newton himself did to light or to anything. You can see that after this was achieved, then we had the century dominated by chemistry in the 19th century. And even the 20th century, you may argue that the first half of the century, physics again was very relevant because we had relativity, we had the origin of quantum mechanics, we had the atomic bomb, we condition this physics progress condition the geopolitics of the planet. Second half, we have definitely biology as really an achievement of humanity. And it is still early, but it is clear that the 21st century is the moment where humans are reaching the understanding of information theory, in particular, classical and quantum information theory. I will try to substantiate this later on. And I do have this idea that the second half of the 21st century will be devoted to ethics, who will somehow reflect on the meaning of this accelerated process. Very many of you may think that this line will end up in something really, really crazy. And the first time that I know this was written in a precise way was by a fantastic mathematician and physicist, which is John von Neumann. He, in 58, he said this famous sentence: "The ever-accelerating progress of technology and changes in the mode of human life give the appearance of approaching some essential singularity in the history of the race, beyond which human affairs, as we know them, could not continue." So whether or not we are approaching a singularity, this is difficult to say. But let me give you ingredients to think that we are really, really making enormous progress. And for that, let me zoom on the 20th century. So these two lines are combining the essential pieces of information theory. So one is artificial intelligence on the bottom and quantum mechanics on the top. So you do have the beginning in 1900, 7th of October of 1900 is the first quantum equation written by Max Planck. But around 26, we had the postulates as we teach them today. So from then on, many things happened. The understanding of solid state, of condensed matter, of quantum optics, of high energy physics, the trying to unify the theories of the universe. So everything has started in those times. So actually, electrodynamics started in the 30s. And then we also started to do applications like the transistor in 47, the laser in the 60s, atomic clocks that go into GPS. And then recently, ideas of how to manipulate information to do computation. And a landmark was factorization algorithm done by Shor, Peter Shor, mathematician, 1994. I added www. You may wonder why. Well, this is because this protocol was invented at CERN, the particle accelerator, to discover new elementary particles, as a protocol to communicate data between the teams. And this is why it's free. Now, in 2005, we have our first quantum gates. So we are really going towards the construction of a quantum computer. And in 2019, Google demonstrated what they call quantum supremacy. Many of us prefer to call it quantum advantage. So we had a first example of computation that could not be done by your classical computer. It was done in 200 seconds on the quantum computer. It would take over 10,000 years on a classical supercomputer. Artificial intelligence has done also an amazing progress. From the 30s, Church passed Turing, the first machines in 46, the theorems by Shannon on how to manipulate information for communication, or the classification of problems as NP versus P, the difficult versus the less difficult in the 70s. There have been plenty of winters for artificial intelligence, but in the 21st century, the introduction of the deep neural networks and the new techniques to train them, it's really spectacular. So nowadays, this advanced artificial intelligence is remarkable, remarkable. And you know, this will go on, and actually we are seeing something which is the merging of quantum mechanics and artificial intelligence in what we call quantum machine learning. So let me go a little ahead. So we try to think that there are like two phases in the quantum revolution. The first phase was achieve during the first 20, in the 20th century. And these are the postulates and the first application: transistors that give rise to computers, lasers that control communications, and many other things, atomic clocks, GPS, magnetic resonance imaging for medicine, which is the control of the spins of the nucleus of the particles. But now we are thinking that we are entering a second revolution. And this is related to the fact that we now have quantum instruments to control quantum systems. So you see, we now have an extreme refinement in the way we deal with quantum matter. And this seems to bring the opportunity to create a completely new category of computers that we call quantum computers, to do quantum communications in a way which is absolutely secure. You cannot break them. That we are doing quantum sensing to precisions that we never thought that would be possible, or quantum simulation. We can simulate quantum systems with other quantum systems. These are examples of the things that we think that we are now able to do. And in this sense, let me pass to my second point, that is CQT, Center for Quantum Technologies in Singapore, and tell you that this is a center where we do all that, where we generate the fundamental knowledge, where we move this frontier of knowledge. Okay, it was something that was not known before, and now it is known because we work there. Or there were things that were impossible to do, and now we do them. Okay, at the most fundamental level, at the single atom level, single photon level. So the center is it's a center with 24 principal investigators, 108 total amount of people, and we have 61 PhD students, growing very fast, and we have a lot of graduate students. So it's a big center, and we are also paying some attention to creating startups. That was never the mission of the center in the first steps, but now this is simply coming naturally. We have created 5 spin-offs in the very last years. So let me tell you what we are doing here in the context of this knowledge at the edge. Well, here you see, this is an image from the group of Murray Barrett. And you may wonder what you're looking here. This is amazingly, it's a clock. You should see the lab. Okay, it's really beautiful in itself. This is nothing. This is a small piece of it. And the racks of electronics controlling this equipment is really amazing. This is really the state of the art. Murray is constructing optical clocks. They are called optical clocks because the frequencies that they deal with are not like a microwave. They produce higher energy jumps, and therefore they can be more refined, higher frequencies. So these clocks that Murray is building are around the precision reaching 1 part in 10 to the 19, 1 and 19 zeros. So if that would be stable, which is not through many centuries, that means that you have a precision of 0.01 second in the age of the universe. This is amazing. So this is how well we can now measure time. It's so precise that if you raise the table of a clock by centimeters, the pace of time changes according to general relativity. So you have to take into account every possible effect to do that. And it's very spectacular. This is for the students who have never entered the labs. This is similar for every lab at the frontier. No? We deal with extreme things. The smallest, the highest energies, the shortest times. We're pushing the boundary. Okay. This is another true picture. And this is belonging to the group of Alex Link. As you may see, let me use my pointer here. You have this little thing. Okay, well, this is you have a nano cube, which is a nano satellite. What is special about this? Well, Alex has managed to put a source of entangled pairs. So we generate this funny thing that quantum mechanics produces, which is correlations uh, that go across space for two different particles. So if one particle can be in spin up and the other is spin down, or vice versa, spin down and spin up, but they are on a superposition of that, he has been able to create entangled particles in space. What is the next step? Well, he's preparing the next generation is that this satellite will send the two photons to different places on Earth. And then when the receivers on Earth get the photons, they can establish secret keys according to quantum mechanics. And therefore, they cannot be broken by any hacker. So again, this is really spectacular to produce all this refined technology in space. Let me give you a third example. This is the lab of Matsukiewicz. And all these optics that you see on the table are there to control an ion. Okay. Now, these ions is amazing again because you trap them because they have an electric charge, but you manipulate the internal degrees of freedom of the atom. So again, it's a manipulation of one by one the atoms. Okay, and let me give you a fourth example, and this is a beautiful picture again. It is golden. I think it's gold actually, the surface. What is this? This is one of the variants of a quantum computer. Actually, it's a little bit of a, of a distraction because the real quantum computer is a chip which is on the bottom of this thing. So what you're seeing here is the fridge. And why it's a fridge? It's called a dilution fridge because then when this is completely sealed, there you gain temperatures, you go down to temperatures of the order of 15 millikelvins. So that's minus 273 degrees. Okay. Why you need to do that? Because it's only when you freeze your environment that the elements you are controlling can develop their quantum properties without being destroyed by the particles which are around. So we need to go to 50 millikelvin to do quantum computations nowadays. And what you are seeing here is all the electronics that eventually, which is microwave electronics, that eventually on the bottom will address the elements that control this information, which are called qubits, quantum bits. It's again really spectacular. Let me mention, given that that we have all these efforts, that we are not isolated, and CQT is a place where we look for knowledge in as many collaborations as possible. So this is a little plot of the island of Singapore with all the elements around, and our 24 principal investigators, many of them have relations with NTU, with Yale NUS College, with our university, with National Institute of Education, and we are even building now new relations to a STAR and to the National Supercomputing Center and whatever, an SUTD. All the possible people around the island, well, we're trying to be in very good relations. And recently, a new program for quantum technologies called QEP is being put forward, and this will be a way to fund all this research. Let me go into the third piece, which is an invitation to research. Again, let me invite students to join any of the projects we have in quantum communication to produce a test bed for Singapore. We want to have really to prepare the island for quantum cryptography, all the island. We want to guarantee that all the optical fibers can support the communication of quantum states. And we are also in the satellite effort. We are trying to go to the next step. And we have collaborations with other countries so that these satellites communicate on different countries. Let me also invite students to add all the efforts we have in quantum sensing. Those are not only the ones at CQT, but the ones that we want to have a relation with. So for instance, NV centers, this is a nitrogen vacancy. Let me tell you an experiment which is very peculiar. So people have been able to take a nano diamond to produce inside the nano diamond one atom of nitrogen that has spin, net spin, whereas the carbon doesn't in this particular case, and a vacancy. This is nitrogen vacancy centers. Well, this becomes a spin which is protected and can sense magnetic fields. And you can even put the protein outside, and the NV center is reading the protein state. So this is really spectacular. We are making microscopes with a single atom. It's really spectacular. Or accelerometers of 1 part in 10 to the minus 9. That's the same as detecting if used as a gravimeter, that detects that the presence of a moving body 500 meters underneath your position. Okay, or well, it's really spectacular. Okay, you can join the idea of producing magnetometers, the best measurements of magnetic fields. And here I bring another idea. We are able nowadays to levitate mesoparticles and charge mesoparticles that when there is a magnetic field, they feel this magnetic field and they are read by an NV center. So you see that the idea of this second revolution, we even use NV centers as an element to read the modification of a levitating particle on a superconducting current. It's like a new world. Or distant measurements like the ones done on to detect gravitational waves that have a precision of 1,000th of an atom over 3 kilometers. Again, really spectacular. And why not quantum computation? Well, a quantum computer, formally, we know that there are algorithms that can break every crypto protocol used nowadays. There is a NIST competition, National Institute of Standards and Technology in the States, doing a competition to have a solution to the problem of a quantum computer breaking all the communications of the planet. But these quantum computers are also expected to produce enormous progress in the design of trucks because they are dealing with they are quantum in themselves and they can simulate quantum states much better. So they can simulate molecules, okay, or finance or optimization problems, or the reunion of quantum mechanics and artificial intelligence, which is many of us are working on that, quantum machine learning. Not bad. And let me also say that we also address the basic science at the theoretical level. So quantum information, we have PIs working on quantum information, condensed matter, high energies, everything which is related to the deep understanding of the laws that we are manipulating. Okay. Of course, this has to be understood. It's a balance between basic and applied research, and CQT is a place where we do balance basic versus applied research. They are complementary. They are not exclusive. My last slide, it's sort of an invitation in the broad sense. Well, although it's obvious that quantum mechanics is useful. Come on, all computers, all lasers, all resonances, all GPS, all that is supported by our understanding of quantum mechanics. So, of course, quantum mechanics is useful. Okay, it may happen that society doesn't know that, but it is, and that's why technology is emerging from only the countries that have profound understanding of research. Okay, all the other countries have to buy the results; they cannot produce it because you need to understand the laws. But this said, I'd like to bring an idea, which is the pleasure of doing research, curiosity-driven research. Forget that it is useful or not. This is secondary. I mean, what you really need is to be good, to understand, to to be on the edge, to dive in whatever you don't know. I mean, you have to understand that there is nothing worse than to be biased against something. So, and this is where you need to be really open in research. There was Heisenberg who used to say that quantum mechanics was a field that would never be developed by authoritarian countries because there would be no way to give the free of spirit, the free of thinking to the researchers. Indeed, it's a fantastic world, the one of research at the edge of the laws of nature. So this is what I wanted to say, and you're extremely welcome to come to CQT.
Thank you, Professor Latorre, for the very interesting and inspiring talk. So there is one question right now, and everyone is welcome to ask questions. Either raise your hands or best typed in the Q&A. So this question is by Vidura. He says, "Great speech, Professor Latorre. Thank you for sharing this information. I would like to know if any applicant is interested in CQT, should they have a theoretical background in physics or any other sciences?"
Well, it depends on what you want to join from theory, from experiments, but nowadays in this edge, like a quantum computer, we do have physicists, we do have engineers, and we do have also mathematicians. So there is a field where we need to build teams. I think this is not exclusive of our research. I think that nowadays in biology or in any other field, teams have to be comprehensive. They have to have all the knowledge available. No? In biology, you need people to understand mathematics to model what you're doing, or statistics, whatever. So in our field, again, this is so. If, of course, if you're a degree in physics, then you can join the research which is more on the physics side. If you have a background in computational science, then you go to algorithms for a quantum computer. If you're an engineer, then you may develop the technology to go at 50 millikelvin. So it is clearly extremely open. May I say that I've been in different places, and the teams that we have created in previously before coming to Singapore, they were multidisciplinary.
Thank you. So is there any space for people who are just biologists? Just a joke.
I think so in a much more applied sense, because biology is now using a lot of sensors. So for instance, one of the top level guys in Europe, Novotny, at ETH, which is a fantastic place in
Mhm.
Zurich, his laboratory has been put in direct contact with the medical school. Precisely because now the new edge is to put sensors in your body. So to start to measure humans at a level that we never imagined.
Wow,
Okay.
that's
Yeah.
interesting.
Yeah.
So there are two more questions. One
Mhm.
from Atif,
Okay.
asking, I could find a couple of PhD projects on the jobs section of the CQT website. Are other PIs hiring PhD students too?
Yeah, we do have a permanent open call. Okay. We evaluate them at different times, but it's open all the time. And the best way is that you address to our web and people, and we have a committee to deal with all the PhD
Yeah.
applications, and you will be very welcome.
So the other question is, what is the by Dishish? What is the scope of for students with a background in material science with knowledge of physics in joining CQT?
Again, there is a branch of quantum research nowadays that deals with materials. Okay, in particular, was for the so-called quantum simulation. Okay, and the idea there is how can we use, for instance, cold gases to simulate materials. Okay, so there is a lot of crossover from theory and ideas to practical research. And I think the best is to address, the student should address himself to the center with these kind of questions, and then he would probably talk to the people who are doing now simulations with off materials. Yeah.
Okay, any other questions? Maybe one last question. Would you encourage someone to do basic or applied for their PhD?
I think that you have to follow your heart. I don't know if I imagine many people have told you. I mean, the most relevant thing in research is to be passionate about what you are doing. You have to when I was a young man, I would if I had an idea, I couldn't sleep. Literally, I spent nights without sleeping because I thought I had the idea. So passion is the engine of science. That's why it's unstoppable. Nobody can avoid somebody to think about ideas. I myself was in basic science in the theory part, but my respect for experiments is beyond belief. I mean, I'm in heart an experimenter. So, and all my students, and I have had many in my life, are training this way. And in particular, now, two of my students, I force them to join experimental work because I don't see why we should. This is like the people that separate art and science and said art versus science, the two cultures. No, come on. We are a common culture. We are humans when we are doing something together. Well, the same. Physics is the same. Is that there is theory and there is experiment. So be everything. Don't try everything.
Okay, thank you very much, Professor
Thank you.
Latorre. The next
You're very
speaker
welcome.